Hey guys, Mr. Backerberg here. In this video, we're going to look at secant and tangent lines. So when we talked about Galileo and rolling a ball down a ramp, the relationship that he came up with was s equals t squared. S being the distance that the ball has traveled and t being time. So the distance is equal to the time squared. And if we look at a graph of this, we're going to look at this function for t values that are greater than or equal to 0. We don't want to go negative when we're talking about time. What's going to end up happening in here is we're going to have the right-hand side of a parabola. Now, if we look at some specific points on this graph, if we looked at a t value of 1, that would give us the ordered pair 1, 1, because 1 squared is 1. And if we looked at a t value of 2, that would give us the ordered pair 2, 4. And I'm going to highlight those points on my graph. So I'm going to say that this is my 1, 1 point right here, and I'm going to say that this is the point 2, 4 right here. Now what I'm going to do with those 2 points that we just plotted out is connect them with a straight line. And that straight line is going to represent the average rate of change, or the average velocity. Now this line is called a secant line because it's intersecting our graph at 2 points. If we wanted to find the slope of this line, or find the average velocity for this function, we can use these ordered pairs that we just came up with and do our delta y over delta x. So I'm going to take 4 minus 1 over 2 minus 1, so we get an average rate of change, or an average velocity of 3. So what that means for us is that the average velocity of this ball traveling down this ramp is 3 feet per second on the interval between 1 and 2 seconds. Now, like the name implies with the average velocity, that just tells us the average velocity of this ball as it's traveling down the ramp, but it doesn't really tell us the velocity of the ball at any specific given time. So what Galileo wanted to do was move these ordered pairs closer and closer together, move these points closer together to try to get the smallest possible gap between the ordered pairs to give us the best approximation for the instantaneous velocity. And what ends up happening in there is, as these points are moving closer and closer together, ideally we'd want to be looking at one specific point. So this slope line right here is just touching my parabola at whatever specific time it is that we're looking at, whatever ordered pair we're looking at. And that's called a tangent line, since that line is only touching our graph at one point. So as we're moving those ordered pairs closer and closer together, essentially what we're doing is a limit problem. So we're going to use limits to help us find the slope of the tangent line to the graph s equals t squared at the point 1, 1. So we're going to look at the limit of our average velocity, and remember that's delta s over delta t, as our t value is approaching 1. So we already know that we're dealing with the ordered pair 1, 1, and remember this limit as t is approaching 1 means that we're moving that second ordered pair closer and closer to that t value of 1. So for our general ordered pair, if I were to take any general t value and plug it into this equation, then the output value is just going to be t squared. So what we're going to end up getting, if we find slope using these two ordered pairs, it's going to be t squared minus 1 over t minus 1. And remember, t is approaching 1. Now on top, we should be able to factor that out. That's a difference of perfect squares. So we're going to get t plus 1 and t minus 1. And then our denominator is still that t minus 1. Now on top and on bottom, because we have those t minus 1s, we're going to be able to cancel those out. So we end up getting t plus 1. Now what we have to remember here is that our t value is infinitely approaching 1. So I can sort of plug 1 in for that t value right there, and we get 2 as the answer. So at the ordered pair 1, 1, we can say that the instantaneous velocity of our ball rolling down this ramp is 2 feet per second. That's going to be it for this video. Thanks for watching.